Okay, so now we're ready for a few field tests that we can do. A lot of the tests that we do are going to be done in the lab, but some of the tests need to be done in the field, like temperature. So the first thing we'll do is to take temperature of the water sample. So here's a bottle for the water that we just collected, and I'm just going to stick a probe in here, measure the temperature, let it stabilize, and looks like it's 16.3 degrees Celsius. So 16.3 degrees, 16.4 degrees, it just changed. So we'll call it 16.4. So we got one sample done, out of the way. We've got 5 other jars that we can keep for use in the lab. Speaking of use in the lab, we have to take one of our sample jars and wrap it with tin foil. The reason we want to do this is so we can keep all the light out of this, and we're going to call this the dark bottle, and we're going to use this to measure our BOD, our biochemical oxygen demand. So what we'll do is we will wait 5 days. This is Thursday, so on Tuesday I will come back after 5 days, and I will measure the dissolved oxygen content in this dark bottle after the 5-day incubation period. We'll compare that with the oxygen content that I measured today in the lab on day 1, and we will subtract them. That way we can get biochemical oxygen demand, or BOD5. The other test that I want to do right here in the field is for total suspended solids. For that, I use this thing called a turbidity tube. Inside the turbidity tube, at the very bottom, if you can see that, there is a black and white shaped disc. It's called a Secchi disc. When you can see the Secchi disc, that means that the water is fairly clear. If the water's dirty enough, then you won't be able to see it. Then we call the water turbid, or it's got a lot of stuff suspended, a lot of solids suspended within the water column. So what I'm going to do is I'm going to grab a sample of that, and we can measure the turbidity. Okay, the water's filled nearly to the top of this turbidity tube, and if I were to look inside the tube right now, I can't see the Secchi disc. So if I were to press on the bottom of this, it's a spring-loaded seal, it's going to let out some water, and the water level is going to drop in the tube. So at this point, I can barely see the Secchi disc. So I'm going to let it out just a little bit. And right now I can see it. So I can barely see it, but I can definitely make out the difference between the light and the dark. And what I will do here is I'll read the water column, and it's 97 centimeters. So I don't know if you can tell where it is, but that's 97. And we will use that in our labs to calculate the turbidity of this particular water sample. If we wanted to, we could calculate, or we could measure total dissolved solids and pH here. I might go ahead and do that real quick, and that way we can do the test in the lab just to compare and see. For that, I have this probe right here. This measures electrical conductivity, which is directly related to the dissolved salts that are in the water. Those are the dissolved solids. And it also measures pH. So I turn it on. I grab my bucket, and right now it's set to pH. It should be. It's set to pH. So put that tube in the water, let it stabilize. I have a pH of 7.26. Also, it gives me water temperature here, 16.5 degrees Celsius. So we were right on with our other thermometer, but 7.23 pH is what I have for that sample. Next thing we'll do is measure total dissolved solids as a measurement of electrical conductivity. This is going to put it in parts per million. (36), and it just went away because I took it out of the water, but 36 parts per million, or parts per million is also the same thing as milligrams per liter. So that's something that you should probably know for future calculations. Milligrams per liter, parts per million, same thing. All right, so what I say, 36 on that one. So those are the field tests. We will see you in the lab to do the rest of them.